All right, so in this tutorial, we're going to continue discussing graphing. We're also going to look a little bit at some special functions to create simulated data with for and while loops. We're going to have further discussion of the for and while loops later on in future tutorials, but this will be a first example of it. We're also going to look at creating crosstab tables, two-way tables and or contingency tables, depending on the terminology you use, and building heat maps from those tables. And then also we're going to look a little bit at the end at dictionaries. Now the dictionary thing is going to seem a little out of place, but it makes a lot more sense in the context of the missing lectures that we're doing for the rest of my course. All right, so to begin with, we're going to import a couple of new functions in order to do our simulations. So I'm going to import a package called math. Again, this is a built-in package, so you don't have to install it. And then also the random package. And then for making some graphs, we're going to use the matplotlib pyplot. Now here I haven't, I've just imported the entire pyplot, and I haven't imported it as an abbreviation. So when I call the package, I will have to type out pyplot each time. Now we're going to simulate some data, using randomness in order to create some fake data that we can plot. And this is frequently a common thing that data scientists will do just to kind of get a feel for how a package or a function operation works on data that's not available to us. We kind of simulate it, and then we can play around with it so that when we get the real data, we have everything already in place. So we're going to create a function, and again, we'll say more about creating functions in future tutorials. But here we're going to define our function. We're going to call it interest normal. So we're going to create an interest function that is normally distributed. And so it varies a little bit. So if you go to the bank, you get a fixed interest rate, and it kind of stays there for a long time. On the other hand, if you're investing in the stock market, then your equivalent interest is going to fluctuate quite a bit because the economy may be good or it may be bad. But there will tend to be historically a range of values that you can get. And so we're going to create a normally distributed interest function. And then we're going to apply that to some sort of principal, some balance in our account, some value for our stock market investment. Now, the rate that we're going to calculate here is the thing that will be random. And this is a normal variate. So this is going to be a normally distributed function. It's going to have a mean of 3%, and it's going to have a standard deviation of 1.5%. And then we're going to return, so what's going to come out of this function is we're going to take the principal that we input, and it's going to multiply by the random rate that was calculated from this random function under a normal distribution. Now that's just so I'm going to run this to put it into memory so that I can call the function. And we're going to use this function to calculate a simulation of what would happen if I started with a particular balance in my account, and then I put it into the stock market, and I had this variable rate happening on my money. And I did that for, a certain amount of time, and 10 years, let's say. And then how much money would I have at the end? But because it's random, different sequences of 10 years will give you slightly different amounts. Maybe different stocks that are normally distributed in the same way would give you slightly different interest rates at different points in time. So we're not going to just run this one time in 10 years and see how much we get. In the simulation, we're actually going to run it 10,000 times to see what would happen. Because again, any one particular run through those 10 years will fall into sort of a range of values, but you won't be able to tell what that range of values is from just one time through. So we're going to run it a bunch of times, And then we'll be able to see sort of how the distribution works. What's the sort of most likely outcome versus what is the least likely outcome, and so forth. You know, what's the high end that we could earn versus the low end that we could earn based on our simulation. Now, we're going to set the number of years in each of our simulations to 10, and then the total number of simulations to 10,000. We're going to create a list, essentially, of values that will be the ending balance for each one of our simulations so that we have a data set that we can plot. And then this is our for loop for I in the range of sims. So this is essentially for each I, for I less than 10,000, do the following. Set time equal to 0. Start with an initial balance of $1,200 for each one of our simulations. And then while time is less than years, you're going to calculate the balance plus the interest. So this interest is going to calculate the interest on that account, again, the random rate from that year, and then it's going to add that interest to the balance. And then it's going to increment the time by 1. And then if time is still less than the 10 years, then it's going to do this again. And it will keep repeating that until you've done this 10 times. And then once it's done that 10 times and time is now greater than 10, then it will calculate that ending balance and append it to this end balance, this list of the ending balances after 10 years. And then finally, when we are finished running this for loop, what we're going to end up with is this end balance is going to not be an empty list. It's going to be a list with 10,000 ending balances. And so from there, we are going to plot it as a histogram. There's 10,000 values. So the rule of thumb for histograms is between 5 and 20 bins. We have a lot of values, so we're going to use 20 bins. And then we're going to show the function. Again, this is using, since we didn't import it as PLT, we imported it just as pyplot. We're going to have to call pyplot rather than PLT, as we did in our previous videos. All right, so then we're going to run this whole cell. And notice how quickly Python was able to calculate 10 steps within each year, 10,000 times, 100,000 calculations of interest rates. And each one of those steps took several operations apiece. And all of a sudden, we almost instantly have this histogram. And so we can see that in some cases, we barely earned any money at all. In a very few cases, we earned like more than $1,850, but you know, as an ending balance. But in most cases, we ended up somewhere around this $1,600 range at the peak of our histogram. Now, we can also, for numerical data, we can also create box plots of numerical data. That's typical if we have a single numerical variable and we want to just get a look at what it looks like in the broad strokes. We're going to create a box plot of that end balance function, again, in pyplot. And so this is our box plot. And notice that it's plotted all of these extreme values. And we have 10,000 values, so there's quite a lot of extreme values being plotted. But we have our extreme values plotted. We have our box in the center. And similar to our histogram, it does appear to be very even and symmetrical on both ends, as you would expect from a normally distributed data. All right, so continuing on with working with that employee data file, we're going to go back to importing pandas and Seaborn, and we're also going to import NumPy. Again, we're going to import this as NP. NumPy is another very common package that a lot of our other packages are built on. And if you want to do certain kinds of operations, NumPy has a lot of functions in it that you can use for that. And then, as we had in previous discussions, we're going to load that same employee data set. Again, anything with a lot of numerical values will work for these demonstrations. Now, if I want to summarize the data into tables, again, I'm going to use my two variables that have the least number of values that are my two like masked numerical variable or my masked categorical variables. And I'm going to build a table. Now, this is using a crosstab function. This crosstab function is going to create essentially a two-way table of the values in my table, in my data frame. Now, the order that you use for education and gender in this case is going to affect the way the table displays. So if I put education and then gender in order, then education will appear in the rows and gender will appear in the columns. On the other hand, if I change the order and I put gender and then education, then education will appear in the columns because it's second, and gender will appear in the rows because it's first. So this is useful in terms of thinking about how the table is going to display, what do you want to be the rows and columns? If one of these has a lot of categories, it may be better to include them in either the row or the column, depending on the amount of space that you have. And by default, this is simply going to count the number of observations in each of the categories. Now, I can use this kind of a summary table in order to make a kind of graph called a heat map. And what a heat map does is basically it's a grid, and then it plots the values in the table in the grid as colors. So I'm going to use table 2, and I'm just going to plot that as a heat map. So here's my education, here's my gender, here's my legend. So it's telling me dark colors are small numbers and light numbers are large numbers. Now this, if you had a much larger grid of values, then you would get a much more interesting looking heat map. But this is one way of displaying information that is a little more visual than, it's more appealing to the human brain than just a simple table. Now, I can also change the default color scheme. So again, you'll want to look at Seaborn's documentation in order to see what other kinds of color palettes are available that you might want to experiment with. In this example, I'm going to add some attributes to my heat map function. So table 2, I'm still plotting the same table. I'm going to add annotations. So that's going to actually tell me what the numbers are directly on the cells. And I'm going to create a line width just to, again, help separate some of the colors that maybe are too similar to each other to really see the distinctions. And the color map I'm going to use, instead of the default that goes from this dark black to this, sort of pale orange, I'm going to use a color map called yellow, green, blue. So one end is going to be yellow, the other end is going to be blue, and it's going to transition through green in the middle. So my small values are this pale yellow. My large values are this dark blue. And then, of course, it goes through green in the middle. And you can see the annotations were added. So the counts are now displayed also on my heat map. And again, this is a more visual way of sort of displaying that same tabular information, but now, that really large number of counts in the middle here kind of pops out a little bit more. Now, there are data structures that we can also encounter that are not just data frames in Python. And so we're going to start looking at a couple of them. And at the end of this tutorial, we're looking at a dictionary. Now, one of the reasons that the dictionary is useful is because it's similar to another kind of data structure we're going to encounter when we import JSON files, which is JSON files are basically dictionaries. And so that's sort of where we're headed, are these other kinds of database type of structures. And so here we're going to create an example of a dictionary. Now, dictionaries are essentially collections of name value pairs. So there is a attribute that has the value or the name, first name. That's the name of the attribute. And then the value of that attribute is Jonathan. So Jonathan Freeman has a first name of Jonathan. His last name is also Freeman. And notice I'm playing sort of fast and loose with the quotation marks, single quotes, double quotes, doesn't particularly matter. You're trying to tell Python that it's a string and that it will accept either one as an indicator that it's a string. We have a login count, so how many times has Jonathan logged into the system? Are they a writer? That's a true. Who do they work with? It's not just a single value in this case, it's a list of different companies. And it turns out that Jonathan has a pet raccoon named Lily. Okay. And so this input structure with the curly brackets, that's going to import our dictionary. So notice that pets is itself a sub-dictionary inside of a list. So if there is more than one pet, then you would have multiple dictionaries of those pet properties separated by commas. But in this case, there's only one pet for Jonathan. And so only one dictionary, sub-dictionary in that list of pets. And then once we've input this value in the set of values, we're then going to print the dictionary. So if I run this, so again, one thing you'll notice here, again, dictionaries are marked by these curly brackets on the outside. We have this sub-dictionary right here, and then we have these lists that occur here and here when the value can take on more than one possible value. So you can have quite complex structures inside your dictionaries. Now, depending on the complexity, you can also convert these dictionaries to data frames. Now, if we were to convert this dictionary to a data frame, some of our columns would have lists in them, which isn't ideal for working with data frames. So before we converted this particular dictionary into a data frame, we would probably want to do some additional processing on it. So for the example of converting dictionaries to data frames, I'm going to use a slightly simpler example. Here, we essentially have a list of computer elements and their cost. So a computer, they're pricing at about $1,500, the monitor at about $300, a printer at $150. You've got to be kidding me. And then a desk at $250. And so these elements, these are my names and my values. Again, your values can take on text strings, or they can take on numerical strings, numerical values. So I'm going to create my dictionary and then display it. So again, you can see this curly bracket on the outside indicating that this is a dictionary. And then I can actually convert my dictionary into a data frame. So my dictionary here, I'm going to call the items from my dictionary, and the names are going to be the products, and the values are going to become the prices. And then I'm going to convert that into a list, and then convert that from the list into a data frame. And then we're going to display the data frame. So as you'll see in future tutorials, we're going to look at JSON particularly, which has the same structure as a dictionary. And if we have the right kind of a structure, then we can take those dictionary items and convert them into a data frame, which we can then manipulate in pandas the same way we manipulated files that we imported from Excel.